Hey guys, so in this short video, we're gonna just talking about the Lenz's law. I started with the state of the Lenz's law, and then we see how to apply that law to identify the direction of the induced current and induced magnetic field. So basically, Lenz's law stated that the loop resists the change of magnetic flux. That means if the magnetic flux increase, the loop try to cancel that increase to keep it at the same. And the situations when the flux decrease and the loop try to replace this one by generate more magnetic field to cancel that decrease or to replace that decrease. Okay. And how to cancel and how to replace those two words, cancel and replace, it's basically by the generating or producing induced current, and which create by induced magnetic field. So basically we create the induced magnetic field and that create the induced magnetic current. So today we're gonna see how we can find induced current and induced magnetic field. Let's start with the example here. We have magnetic field, we have the conductors and the rod move in the conductors, and that movement go to the left side. Here is the initial condition, here is the second case. So in that case here, once the rod go to the left side, the area of the loop will be decreased. So as a result, the first question asks you for the flux through the loop is changed. So here, since the area is decreased, so basically we have, yes, the flux is decreased. So based on the Lenz's law, we see that flux is decreased. So right now I am in this case. What happened is the loop will try to replace it. So what's that mean exactly? So here's the case we are talking about. So we are in the decrease case. What's that mean? The loop will try to generate induced magnetic field to replace that loop decreasing. So generate more magnetic field to replace that one. So that's the lead us to second questions. What the direction of the induced magnetic field? Since here is to replace, so the direction of the induced magnetic field will be the same direction of magnetic field. So into the page. Main thing to replace that decrease. Okay, the second questions here, the direction of induced magnetic field, you already find it here, and what the direction of the induced current. So induced current, we're going to use the right hand. So we have, here is the rod moving that direction, magnetic field point to the base, and we're going to use right hand in both paths. So this path here, and lower path, and upper path. So according for the right hand, where is your current pointed to your thumb, and your magnetic field pointed to the base. So we find the current, induced current, go in this direction, in that side here. And from here go the up direction. So to complete the loop will be in this loop. So that the directions here for the induced current, which clockwise direction. Now here's this talking about from the perspective, we know how to identify the induced current or the current directions based on the magnetic field using motional EMF. According for the Lenz's law, in that case, so we have the current clockwise. Oh, that's the current what we find using the Lenz's law. Now let's see how we can find it using the emotional EMF. We're going to use the right hand again. And where is my thumb pointed to the velocity and my magnetic field point to the page. So we find the force pointed up in the positive direction. So in the positive charge. So if I have positive charge here, the force will be pointed down. So that means the positive charge will be collected here, and negative charge will be here. According for that, the direction of the current will be in that direction, the same direction of current in the second case, or in the Lenz's law. So either way, you can use to identify the direction of current or induced current. But Lenz's law is more general. Let's see the second case. So we have the same example. Now the only thing is the rod is moving the right side instead to the left side. So here is the initial case, and here's the final case. In final case, what do we have? We have the area, it's bigger. So the area is bigger, that lead to what the magnetic field will be increased. So when we have the increased magnetic field, so according for Lenz's law, I am in this case. What happened? What the loop they're gonna be, what does? It will be try to cancel that increase. How to try to cancel that increase? We have the magnetic field point to the base, so we're gonna be generate a magnetic field, and that magnetic field point out of the base, just to cancel that increase, not to cancel the entire magnetic field. Okay, so we're gonna be generate the induced magnetic field point out of the base. That's out of the base. Here will be out of the base. Sorry about that. Here is the out of the base. Now, what regarding for the direction of the induced current? How we can find the direction of the induced current in that case? Okay, we're gonna use the right hand again, the same thing here. So the direction of the current, you will find it go in that part here, and this one here. If I finish our loop, will be pointed this directions here, and this direction is here. So this one is here, the direction of the induced current, counterclockwise directions. Again, we're gonna compare them with the EMF. So we find this one in using the Lenz's law, the direction of the induced current will be counterclockwise. We're gonna use the same approach, but we're using the right hand when we use the EMF. Velocity go to the right, magnetic field point to the base, force up. So again, positive charge, we're gonna be, here is the positive go here. And in that case, the negative go in that directions. The current will be follow the direction of the positive charge. So we have counterclockwise in both cases. Okay, that's how to comparing or how to apply the Lenz's law to find induced current and induced magnetic field. Thank you so much, guys.